Essay question number 2. Osmosis is when water moves through a selectively permeable membrane. It moves from a side of low solute to high solute, so water follows solute always. And only the water should move. No solute moves, and the water will move until it either is equalized in concentration or until an external force like pressure stops water from moving. Osmolarity is defined as the number of moles of particles per liter of solution, where molarity is the number of molecules per liter of solution. So they differ because a molecule of sodium chloride, NaCl, will break into 2 in water. And so you'll have 1 particle of sodium and 1 particle of chloride in a liter of solution, whereas that same particle is considered 1 molecule in 1 liter of water. So osmolarity and molarity differ in terms of how they break apart. 1 molecule of glucose would not break apart in water, so it would be the same. It would be 1 osmol and 1 mole of glucose per liter of water because it doesn't break apart. Tonicity is defined as the firmness of the tissue that it's in this case we talk about cells, like red blood cells. So the tonicity is how firm or how stretchy the tissue is. And solutions can be hyper, iso, or hypo osmotic or tonic. Hyper means more, iso is the same, and hypo is less than. And so you describe each of these in terms of a reference point. So a solution that is permeable to a substance, we'll have this be our cell, and so this is the ICF of the cell, and then all of this on the ECF. If there's a solution out here that is permeable, it will move into the cell. And this is an isoosmotic solution, so it's the same in both the solutions are, but it would move into the cell because it is permeable for the cell. Water would then also follow through aquaporins into the cell, and from there the tonicity of the cell would then be hypotonic, so it would be less than the outside. It would most likely cause it would swell and most likely burst the cell. The resting membrane potential is known as the RMP. It is established using the equalization of the electro and chemical gradients across the membrane. We'll use the fish tank example. Giving this a permeable membrane, so side A and side B. If side B is filled with potassium and chloride cells, but this membrane is only permeable to cations, so only the positively charged ions like potassium in a cell. These will start to move across the membrane. So this side will start to fill up with potassiums, and as this does chemically move, the ions carry a charge, and that creates an electrical gradient as well. With them opposing each other, it creates the electrochemical gradient, which establishes an equilibrium between 2 sides that represent the intracellular and extracellular fluid. As these particles have established their new electrochemical equilibrium, in the case of a cell, there are channels here called leak channels that allow potassium to leave. But in the real example of a cell, there's also plenty of sodium because of the sodium-potassium ATPase pump on the outside. For every one of those pumps, 2 potassium comes in, 3 sodium goes out. At that point, sodium is building up, but because there's no leak channels allowing sodium to enter, the potassium starts to leak out of the cell, leaving a negative charge inside. When that charge has built up enough, it creates and equalizes to a resting membrane potential. It can be seen in a graph like this. If we're starting at 0, as the electrochemical gradient starts to establish, it starts to move down into negative territory, and then as the potassium leaks out, it equalizes, and this becomes our resting membrane potential. The conditions that can affect this are the ion concentrations, how many of them there are, and their permeability in the cell. Like in the case of potassium, it's very permeable because of the leak channels that let it in, and the active transport also, the active transport lets it in. The leak channels can let it out very easily. This can all also be driven by the Nernst equation. The Nernst equation tells us the voltage potential across the membrane. It's not a perfect equation because it is set up using a perfect scenario, but things won't dissociate completely. So that equation is that E equals negative 61.5 millivolts divided by Z, and Z is the charge of the ion. So potassium is +1, calcium is +2, chloride would be -1, and then it's times the log of the ions in divided by the ions out. As the ions move in and out, we can use this to get a value that represents the voltage across the membrane in a perfect environment. We can use that number to plug it into the driving force equation. The driving force is determined by, so I'll abbreviate driving force as DF. The driving force is determined by taking the voltage of the membrane and subtracting that from the equilibrium potential that we got from the Nernst equation, so minus that E value right here. We subtract those two numbers and we will get obviously a new number. If that number that we get is the same sign, so positive or negative, of the ion that we started with, so if the final answer becomes positive and we are using potassium, then the ion will be moving out of the cell. If we got a negative number from the driving force and we're using potassium that's a positive ion, it would be moving into the cell.